Swayam Prabha. Digital India. Educated India.
Hello everyone, we are continuing our discussion on combustion of metals. In the previous lectures, I think we have talked about in detail regarding the ignition and combustion of boron particles, and if we recall our previous discussions on the Glassman criteria, that some particles or some metals can burn heterogeneously, whereas the other metals can burn homogeneously. Now, based on the Glassman criteria, what we understood that if the volatilization temperature of the oxides is greater than the metal boiling point temperature, then there is a possibility that metal can burn in vapor phase or homogeneous mode, whereas if the metal boiling point temperature is higher than the oxides volatilization temperature, then the metal can proceed burning in heterogeneously. So, in that context, the boron particles combustion happen in heterogeneous mode, or surface reactions can happen heterogeneously. In case of aluminum particles, if we recall, the boiling point temperature of aluminum oxide is actually lower than the melting point temperature of metal boiling point temperature is much lower than the oxides boiling point temperature. So, in case of aluminum, the homogeneous combustion is going to take place. So, you just please refer to the table what we already discussed. So, basically what is going to happen, the adiabatic flame temperature of aluminum, the combustion is going to typically greater than the boiling point temperature of aluminum. So, the flame temperature for aluminum is going to be greater than the boiling point temperature of aluminum. So, we can expect that the heat feedback from the flame is going to cause aluminum to vaporize and is going to have like the vapor phase combustion or homogeneous combustion. If you remember, the typical values we had for the boiling point of aluminum is around 2791 Kelvin. So, there is a chance that this is at 1 atmosphere pressure. So, there is a chance that flame temperature can go as high as like 4000 Kelvin, which is easily can evaporate the aluminum. So, at the particle surface, the aluminum can evaporate and the vapor of aluminum is going to burn homogeneously in the gas phase. So, we can see that some flame is going to happen at a distance from the particle surface. Of course, if we recall our discussion also, that we have talked about like aluminum plus oxygen as the oxidizer, but if you change the oxidizer, there is a possibility of transition from homogeneous combustion to heterogeneous combustion. As we recall that if we burn aluminum particles in presence of CO2, then of course the adiabatic flame temperature will be much lower than the boiling point temperature of aluminum. So, in that case it can have like heterogeneous combustion. Whereas, if we just consider the aluminum plus oxygen, in oxygen environment we can expect that the combustion will take place homogeneously. So, the particle is going to have, it will have some kind of a detached flame like this with the smoke trail we can see here. So, we will talk this in detail, But before going into that, what is exactly the application of aluminum particles in the rocket motor? If you see, we have talked about the propellant ingredients, and there we have mentioned that HTPB is considered to be the binder, ammonium perchlorate was considered to be the oxidizer, and aluminum particles were considered to be the metal fuel, if you recall, with some other curing, small quantity of curing agent or plasticizers are used. So, if you look at the propellant surface, typically the propellant will consist of the ammonium perchlorate, and there will be some aluminum particles present into it. I am just putting it, these are like micron size aluminum particles. So, aluminum particles are dispersed within the propellant matrix. So, as you recall, for a composite propellant there is a triple flame structures. So, initially it will have some ammonium perchlorate premix flame. The HTPB binder fuel vapor is going to pyrolyze and vaporize, it is going to produce fuel vapor that is going to mixed with the oxidizing vapor, and they will create some primary diffusion flame. So, this is your APPF, is going to create some primary diffusion flame. So, this is like PDF, and then we have the final diffusion flame or SDF. This was the triple flame structures we understood in the discussion during the burning of composite propellant. Now, the particles, aluminum particles are actually coming out. So, if you look at here separately, so the flame zone is somewhere over here. So, aluminum particles are coming out and they are burning in the flame zone. So, the temperature is very high enough. So, the agglomerated molten particles are actually at the surface, it is going to lift off from the propellant surface, and since there is a flame, there is a combustion gas. So, it will be entrained by the gases and it will undergo the combustion. So, if you look at each of the flame, each of the particles, they will have this type of envelope flame. Now, what is going to happen that during the combustion of aluminum, some oxide is going to form, some native oxide may also present on the particle surface. So, during the combustion, some fraction of the oxide is going to diffuse back. So, if you look at closely, some of the oxide is going to diffuse back, and so it was like a capping of the particle was there. So, some of the oxides is going to diffuse back and deposit onto the particle surface, which actually going to merge with the. So, initially let us say there was a particle surface, there was a native oxide layer. So, as the flame go on, the aluminum particles is actually burning, some of the oxides are actually going to merge with this native oxide cap and is going to increase the thickness here. Now, due to the surface tension force, it is going to pull off and the oxide together to the oxide cap, and it is going to separate from the molten particle. So, this is your aluminum, the temperature is high enough. So, the aluminum becomes like a molten aluminum. So, the cap is actually separating out near to the bottom, and of course, some of the fraction of the B2O3 can also some of the fraction of the Al2O3 can actually go and evaporate as well. So, that will actually lead some of the places where aluminum can actually react with that, and the oxide smoke is going to come out and it can create some white trail. Sometime it has been observed that these particles and smoke is going to actually dampen the acoustic instabilities in a rocket motor. So, the amount of smoke produced during the combustion of aluminum is kind of important, because that is going to interact with the acoustic instability in the rocket motor, and it has been observed that somehow it is going to mitigate or is going to dampen the acoustic instability. Now, the oxide cap can also lead to some fragmentation, jetting effect from the particles. This is is going to form some crack and is going to lead to the oxidation of aluminum and is going to react with the oxygen. So, if we recall our discussion that if we compare the burning of metal particles with the burning of liquid fuel droplet, it cannot be exactly simulate with the metal particle like the aluminum particle case, just because the oxide capping is actually not allowing the full burning or exposing the complete aluminum molten aluminum to burn in the oxidizing environment. So, we cannot really compare this with the normal hydrocarbon fuel droplet where we have the envelope flame, but here there is a problem that some of the part of the aluminum is actually covered with this oxide cap. So, just one to one comparison is kind of not possible, because it is the mass transfer or the mass consumption rate is not distributed, because the oxide capping is actually covering some part of the molten oxide. If you look little closely, what are the model exists there. So, this is the typical smoke trail. So, what I was talking about, that if this is the aluminum particle, so oxide cap is going to come here and is going to cover at the bottom of the particle. So, this is the oxide cap. So, this is going to, you may see that oxide products are actually there. Some of the oxides are actually diffusing back and it is merged with the oxide cap. So, it is covering some of the molten aluminum, which is actually not exactly same as the hydrocarbon fuel droplet, but of course, the metal aluminum is going to evaporate, the vaporized aluminum will be there. There will be oxide products like ALO, ALO2, intermediate oxides product. So, this is typically the flame zone. And of course, the species diffusion will take place like oxygen, hydrogen, CO2, CO, hydrogen also. There will be some heat radiation, conduction of heat is also going to happen due to the conduction through the gas. Okay. So, this I am talking about taking out some is kind of an exaggerated view of any of these particles. So, what I have just shown here is this. If you look at how the each of the aluminum particles are burning in the gas entrainment, because there is a flame. So, the particles is going to burn in the gas phase, and if you look at each of the aluminum particles, this is the typical model of the physical model of the burning of aluminum particles, where we can see that there will be a smoke trail covering the particles. It is some the flame is somewhere distant from the particle surface, because as we said that it is the the particle surface to vaporize and vapor proceeds homogeneously. So, this is the vaporized aluminum which is proceeds homogeneously in the gas phase and is going to burn at some distance from the particle surface, which is creating this envelope flame, and we can see the smoke trail also. Now, aluminum suboxides condense to form the liquid aluminum oxide. Due to the heat release from the flame jolt, if it is sufficient, this is going to dissociate some of the molten aluminum oxide. Now, the maximum temperature at the dissociation temperature of the oxide is going to maintain until all the oxides are dissociated. Now, the position of the flame zone, like where the flame is going to stay or the thickness of the flame zone, is going to be the function of the oxidizer concentration and the pressure in the chamber or pressure in the location. So, that will tell us what will be the location of the flame zone. However, this is like a generalized model of the burning of aluminum in the propellant containing HTPB AP or composite propellant, where each particle is actually having this type of burning profile. Now, one can actually think of the particles may have like micron size aluminum or nano size aluminum. So, due to the size effect, there may be different stages of burning also, like in some cases how the heat transfer is going to take place, how the diffusion is going to take place. So, various stages of oxidations can exist. Depending on the how the heat transfer from the gas to the particle is taking place. Now, the heat and mass diffusion inside the particle is going to also happen, how the melting of the aluminum core is happening, how the phase transformation is happening in the oxide layer, how the oxide layer is going to crack and leading the oxidate to react with the molten aluminum. So, that all is actually influence the mechanism, how the mass diffusion across the oxide layer is taking place, how the heterogeneous chemical reactions like aluminum with oxygen is going to take place. All is going to influence the burning of aluminum particles. So, stages of oxidations is going to vary as per the literature for different size of particles. So, for micron size particles and nano size particles, they are going to different due to the particle size. Now, of course, these cracks and opening is going to give the pathway for the molten aluminum to react with oxidizing gas, and that will result in energy release, and eventually this is going to important for the ignition of the particles. Now, in case of micron size particles, because the size is bigger comparatively with the nano size particles, the ignition may not be achieved because of that high volumetric heat capacity. So, the stages of oxidations may vary between the micron size particles and nano size particles. So, the comparison between the micron size particles and nano size particles, I suggest that the participants can refer to literature on detailed literature on aluminum particle combustion for containing like the micron size versus nano size. One can get more detailed idea about what are the different stages of oxidations happening, but in general, as I said, that it involves this type of features, and I am just trying to relate that what is exactly happening in a composite propellant containing aluminum particles as fuel in a HTPB AP based composite propellant. So, if you look at typically one single particles, that will behave like this type of features. Okay. And as per the Glassman's criteria, we have said that this is like aluminum particle is going to burn homogeneously, or the gas phase reaction can take place, whereas in case of boron particles we have said that heterogeneous reaction can take place as per the Glassman criteria. Now, I just want to give you some glimpse of ideas what various studies are being conducted. This is I am going to show you some of the glimpse of results we obtain in our laboratory. If you recall, during the introduction I had promised that I will show you some of the results obtained from my research groups. So, they have conducted various experiments involving like boron particles loaded in liquid fuel. So, this is what you are seeing right now. It is the burning of a single droplet. It is a single droplet hanged on a quartz fiber, and that droplet containing the jet fuel or just representative hydrocarbon fuel plus boron particles. And these are typically experiments are conducted there, that you just ignite the particles, let the particle burns. So, we have conducted this experiment for various commercially available particles. So, the features are actually different. If you look closely, that you see the particles are actually, so the typical yellow flame are actually due to the burning of hydrocarbon fuel or the jet fuel, and you can look at the typical features of boron burning, which is having like the green flame. So, particles are actually coming out and burning in the flame zone, and it is creating that green flame. So, the idea behind this is, if you recall that once we compare the heating value of various metal particles, what we told ourselves that if boron has high volumetric energy content, can we really mix boron particles in liquid fuel or in solid fuels. So, this is one such idea, and we try to see if we just look at the droplet combustion, how the particles are burning in a single droplet. So, this is a typical droplet combustion features. We tried to plot this d diameter square versus time. Remember, this we tried to relate with the d square law. So, we tried to plot this d by d0 square versus time, and it is not exactly same as the hydrocarbon droplet, but of course, it is following some linear trend with some fluctuations, because the droplet diameter is actually swelling and contracting, because you can see there is a swelling and contraction of diameter is happening, and some of the areas there are ejections, particles are coming out. So, those are called like micro explosions due to the internal vapor formation. They are trying to shattering the droplet and causing the droplet to fragment. Okay. So, this is typical droplet combustion features which we conducted in our laboratory. The other thing is like how the micro explosion and secondary atomization are taking place, because once you mix particles in a liquid droplet, once you try to evaporate them, the particles will try to agglomerate in the droplet surface, and they are going to create some kind of a layer which is actually does not let the vapor to come out. So, depending on the morphology of the particles, this layer maybe have like a impermeable layer, depending on the particle structures, whether it is a amorphous particles or crystalline particle. So, that will lead to high vapor pressure inside this domain, and that will cause to breakup of the droplet, which is possible mechanism for micro explosions as reported there by one of my student. Now, we had also conducted boron loaded jet fuel in a spray combustion environment, because ultimately what our role is that we want to mix the particles into liquid fuel, and we try to burn in a combustor environment just to see whether the liquid as the liquid fuel is burning, whether you are able to burn the boron particles or not. So, this is a typical swell stabilized spray combustion setup, where we actually burning boron as a slurry. So, we have like boron loaded in liquid fuel. So, what essentially we are doing, we are just injecting the boron particles through liquid fuel. So, there is a spray. So, we are expecting once you ignite this, we are expecting that the boron should burn here. We should measure the temperature and just to see whether it is giving any energy release or not. We are not going into the detail of it. I just want to give you some glimpse of ideas that if we can load boron particles into liquid fuels, how we are going to see that how the boron particles are burning. So, this is a typical experimental approach through which we can see how the boron particles are burning. The other approach, so I can show you some results from the from the experiments that typical liquid fuel is going to burn just like a green yellow flame, whereas the boron particle burning is containing that yellow then white, which is boron combustion, and that green envelope which is going to give us the emission of BO2. As we mentioned in previous lecture that BO2 emission corresponds to the emission from the BO2 emission corresponds to the one of the intermediate species, and that gives the green light. So, typically we can perform the various measurements like spectroscopic measurement, we can conduct the temperature measurement just to see whether boron particles have burned properly or not. So, these are the approaches one can look at, that how the particles can be loaded in liquid fuel and you can burn it. So, I will just show you some video from the experiment as well after completing this PPT. So, now the problem of boron particles, if you load in a typical liquid fuel system, what is going to happen? You have let us say liquid fuel, you are trying to load some solid particles. So, you are churning it maybe with some thing, you may add some kind of a surfactant or some ingredients which can actually lead to have improvement of stability of the particles, but after some time it may so happen that particle is going to sediment. So, you may see that you have a clear liquid and at the bottom the particles are actually settled down, which is not really expected. I mean expected in the sense which is not really the requirement for particle loaded fuel, because we want that particle to be dispersed. So, just with the normal liquid you cannot actually have it stabilize the particles for a longer period of time. What you can do is we can actually either do some modification that the particles settle down for longer period of time or do not settle at all. One of the options can be you can make the liquid into gel. So, make the liquid into gel and hold the particles in that gel matrix, so that the particles is not going to settle down. So, you may see that particles are almost staying there, but now you are actually making more complex in the system, because atomizing the gel will be much difficult than the liquid fuel. So, that is another problem we are bringing in the system. We have made the gel, but now how to atomize them properly and burn them properly. So, these are some of the droplet combustion studies conducted by one of my researchers, that they have loaded boron particles in a gel fuel and they burn the droplet. You can see that typical burning of boron loaded cases, you can see green light is shown here. So, this is with normal air atmosphere, but if you increase the percentage of oxygen there, you see this is conducted at 50% oxygen and 50% nitrogen. This was conducted at 100% oxygen. So, once we increase the percentage of oxygen in the ambient, you can see that the oxidation of boron is much more efficient. As you can see, it is a tremendous amount of green light is produced here. It is like a vigorous burning of particle is taking place. So, as you increase the oxygen percentage even more, you can see the intensity of the burning is even higher. So, that way you can see, and on top of that you can see it has been observed that I think it was shown in the same picture actually. Anyway, so Basically, we are trying to show here that once you increase the oxygen percentage, it is going to increase the burning of boron particles. On the other hand, if you see, in this case we have used the magnesium as one of the additives. If you recall that to improve the ignition of boron particles, what we said that researchers have shown that easily ignitable metals can actually improve its ignitability. So, you can see if you use the magnesium as the additive, we can actually improve the ignition of boron particles. So, these are different ways that boron particles can be applied. Now, I just want to complete this by showing you some of the applications for boron based fuels. Now, these applications can be ducted rocket with a hybrid gas generator, like we can use the solid fuels loaded with boron particles, we can use some oxidizers, the partially burned product can come into a ram combustor. So, basically this is a dual combustor mode. So, it is going to further burn here, and the high temperature high pressure gas is going to come here through the nozzle and is going to expand and give the high velocity jet. So, whole idea is that if you want to utilize boron particles, we must have to complete the combustion of boron particles, then only the full energetic potential can be utilized. The other applications can be like marine applications, where water augmented hybrid propellant ram rocket. There also we can think of using some energetic particles, and we can try to burn the fuel in terms of the fuel grain. Here, as you see here actually we are going to add the particles while making the fuel grain, we can actually add particles. Here also we are actually adding the energetic particles. So, the metal fuels can be added to increase the energy density of the fuel. So, there are various applications where we can see metal has tremendous application potential. This is one news articles we have just encountered, that boron powered Chinese missile will work in the air and underwater. So, you can just look at this one. This is like a very futuristic idea that the boron powered missile can actually work both in water and air. So, this is like a in a dual mode, it can be operational. So, what kind of fuel combinations they are trying, so that they can use boron particles into the solid fuel matrix, and that can be used in both marine application as well in air. So, this is like a ambitious project we can say. So, I think with that we close this discussion on the application of energetic particles or energetic metals in propulsion application. I mean, I can tell you that there is a huge research scopes in this area. So, if someone is interested to explore further on this one can actually look at the literature, what are the different work is going on in this area, and how the ways the researchers are finding ways to improve the ignition and combustion of boron particles in order to utilize the boron particles in propulsion application. So, before we stop, I would, as I promised, I would show you some video. So, this is typically a hydrocarbon flame. As I told you, this is just a jet 1 flame. So, you can see the typical bluish flame is shown here. So, this is typically a combustor which is having like optical axis. So, you can look at it. So, this is a typical flame, just neat jet A1. Now, if you just simply load boron particles into the liquid fuel, how is going to burn? You see, it is completely different. You see what I told you earlier, that the boron particles burning having like bright yellow, white glow, and the green emission is due to the formation of BO2, or BO2 is actually responsible for having the green light here. So, this is typically the flame containing boron particles in jet A1. Okay. So, I think with that we close our discussion on this part. I have one more video to show you just with the solid fuel burned in a rocket firing mode. So, you can see this is a typical features containing the boron particles burning. You see the green hue is shown here. Okay. So, I think there is a lot of scope in this area. one can actually look at it. If they are interested, they can look through the literature. Interested to work on, they can find some interesting problem statement and how to utilize the boron particles in practical propulsion systems. Okay. So, with that I think we close our both the modules on metal particle combustion. Now, we will just wait to complete the last module, which is the erosive burning in the week 8. Thank you.